Hi, my name is Justin Allen, and I work at the Lawrence Livermore National Lab along with Dave Knapp and Kristine Monteith. And we worked on using machine learning to predict what processes were running on host machines looking only at network data. This is important for cybersecurity analysts and network admins who need to know what's happening on their networks. That can require host-based sensors for more complicated analysis, but those are often costly, complicated, and can be infeasible in many environments. Many others have used machine learning to predict network traffic. There have been unsupervised methods using k-means clustering, supervised methods using naive Bayes, decision trees, neural networks, and more. However, a lot of these previously mentioned techniques lack fidelity. They were only classified into broad application types like FTP and HTTP, but higher fidelity classifications, like classifying into Chrome, Outlook, by specific process, are less common, likely due to lack of available data sets. However, some do exist, like in 2009, using packet size distributions and port numbers, others looking at encrypted mobile traffic, and the field of browser fingerprinting to attempt to differentiate specific browsers from traffic. Our data set consists of aggregate packet flow statistics on over 1,200 Windows users in an enterprise environment. These sensors can monitor network traffic and every 10 seconds are able to associate it back to the process that generated it. The full data set was over 565 million instances of process execution. However, some of these processes, like SVC hosts, were very talkative, and so we instead took a random sample up to 50,000 examples from the over 1,400 unique processes. Our features consisted of aggregate packet flow statistics. They're aggregated based on each instance of process execution. And we chose two very common machine learning models, random forest implemented in sklearn and multilayer perceptrons implemented in Keras. Batch normalization was used on the MLPs to help prevent overfitting. And since many of the features had very large byte and packet counts, those features were binned and one-hot encoded for the MLP. For each experiment, we had an 80-20 training test set split. For our first experiment, we attempted to differentiate browser and non-browser traffic. So all browser traffic from Chrome, Firefox, Internet Explorer, and Microsoft Edge were labeled positive. And the overall identification accuracy of both models were over 88%. At the bottom here, we have the confusion matrix for both the random forest and the NLP, both of them very similar. Our second experiment was on browser fingerprinting, so identifying the specific browser from known browser traffic. But again, both the random forest and NLPs have very similar accuracies. And in the confusion matrices, we can see that Internet Explorer and Microsoft Edge were often confused for one another in both the random forest and NLP, and the random forest tended to default to Firefox in its predictions. Our third experiment was combining the previous two experiments to do browser fingerprinting along with non-browser traffic, and it didn't hinder performance at all, really. Both models still achieved over 71% identification accuracy. And again, Internet Explorer and Microsoft Edge often confused for one another in the random forest, defaulting to predicting Firefox. But adding in the other processes didn't hinder performance. Our final experiment was predicting process names for all processes with at least 300 examples. This gave us over 480 unique processes. And here's where the random forests and MLPs tend to differ in accuracy. The MLP seemed to handle the task a lot better than the random forest. At the bottom, we have the confusion matrix, where the processes are ordered from left to right based on the number of examples in the data set. So at the top left, we have we have processes with many examples, and at the bottom right, fewer examples, going down to about 300. These processes have a stronger diagonal up here near the top left with more examples, and it gets weaker as we get to fewer. However, there are still some processes with as few as 300 examples that are being accurately identified with over 480 competing processes. This was extended to the top N processes, where N is ordered from based on the number of examples in the data set, going from N as small as a few up to 1,000. And we can see these dips at around 15 to 20 processes, and again around 150 to 200 before evening out, likely due to the class skew, as when we look at the average precision per class and average recall per class, we see again the dips at around 15 to 20 and 150 to 200, and then steadily decreasing as we add in more processes with few examples. We've shown the efficacy of a couple of very common machine learning algorithms on application-specific network traffic classification for many processes. They achieved 88% identification accuracy on browser versus non-browser, low to mid 70% on browser fingerprinting, and about 70% on classification of over 480 processes. The MLPs in random forests had very similar results on few processes, but the MLPs seemed to work better for a large number of unique processes. And they're able to classify some with as few as 300 examples and over 480 competing processes. We established a proof of concept for the identification of many host processes using only their network traffic. However, further work is needed to determine the generalizability, which can be hard to determine given the privacy and security concerns that prevent mass sharing of this data set. However, future work shows that this idea is generalizable. Then models could be trained in highly instrumented environments and deployed in less instrumented ones. Further work is also needed to determine the suitability of this for cyber defense. Questions can be asked like, do processes change depending on version and system version, and do processes change behavior based on a specific threat or malware being deployed? And that concludes the presentation, so we'll open it up to the Q&A now. Thanks.